Alright, part 3 of the standard normal distribution. We're looking at properties of the curve, of the graph, of the distribution. And they're due to the symmetrical nature of the normal distribution about the mean. It can be established that 68%, approximately 68%, of the population will fall within one standard deviation of the mean in a normal distribution. So that, written as a probability, that's the probability between the mean minus standard deviation and up to the mean plus a standard deviation. So that's got a probability of about 0.68. Two standard deviations, approximately 95% of the population of the sample will fall within two standard deviations of the mean. Okay, written the same way except for it's mu minus 2 sigma and mu plus 2 sigma. Okay, and as a probability that's approximately going to be 0.95. So we could say that a randomly chosen member of the population will most likely be, or highly likely be, within two standard deviations, because that's 95% of the population, so that's highly likely if one is chosen at random, because x is a random variable, isn't it? And the third and final one, approximately 99.7% of the population will fall within three standard deviations of the mean. So that's from 3 before the mean up to 3 after. That's 6 standard deviations in total. So 0.997 as a probability is approximately what it is. And altogether, these facts are often called the empirical rule, or clunky 60, 95, 99.7% rule. That doesn't exactly roll off the tongue, does it? So the numbers are handy to remember. We can make statements about a population just by remembering those numbers, and the empirical rule is what it's called. Okay, what it's often called. So graphing these three, let's have a look at them. So the situation where we have 68% of the population, that occurs, there's your mean there, and this scale is in standard deviations. Alright, so the increments are numbers of standard deviations, so there's the mean there at 0, and up to one either side, i.e. two standard deviations in total, one either side of the mean, that's 68% of the population. Okay, written alternatively, you can see that we have mu the mean, and the mean take one standard deviation minus sigma, that is, and mu plus sigma, in other words the mean plus one standard deviation. Okay, and as a probability it's 0.68. And just quickly, we can see for two standard deviations either side of the mean, 95%, or as a probability 0.95 using the alternative notation. And lastly, three either side, total of 6 standard deviations, 99.7% of the population, or 0.997 as a probability. Okay, so we would say that heck, just about all of them are there. It's an extremely high probability of choosing a member of the population within 3 standard deviations of the mean. Okay, very highly likely. We have a sort of example here. IQ tests are often used in the sense they can be assumed to be normally distributed. Now, cautionary note here, IQ is actually written, well, it is actually presented as discrete quantities, alright, because they're integer values. Okay, to my knowledge, they're integer values, they're not real values. Okay, so positive integers. Yeah, but we'll see in future videos we can approximate these things quite well as continuous functions, despite being actually discrete in nature. Okay, more about that in the future, but if you can accept that for now, we have an IQ score graph there. We don't have z-scores on this axis, we actually have the actual test IQ score, and we've got the mean equals 100 and the standard deviation is 15. Okay, and an alternate scale down there in terms of standard deviations is presented as well if you like. So, two questions. What percentage of the distribution lies within 1, 2, and 3 standard deviations of the mean? Well, it's just basically regurgitating what we've been going on about for the last couple of minutes. So 68% for 1 standard deviation, 95% for 2, and 99.7% for 3 standard deviations from the mean. Okay, so what percentage of the scores are more than 2 standard deviations above or below? So more. So we have 2 standard deviations here. So, and it makes sense too because we're looking at 2 lots of standard deviations. That's 2 lots of 15 above 100. Okay, that's 30 and 30 below. So looking in there, we know that that actually is a, well, they're in percentages here, so I'm not going to work as a probability. So percentage, we're looking at 95%. Okay, out here and out there, that's combined to make 5%, which is effectively our answer. Okay, because it's OR, so we're adding them together. And so what we're using symmetry, right? Pay attention, using symmetry. Remember from when we started the video, we mentioned that symmetry. Okay, so symmetry, 2.5% either side. So it's 2.5% plus 2.5%, which is 5%. In total, okay, 2.5% each side. Okay, so we've got another question to finish off our examples. Suppose that Z is a standard random variable, and so we know the mean is 0 and the standard deviation is 1. Find the probability that Z is greater than 1. Now we could do this in 2 ways, and we've already done it using the graphics calculator before, so I'll show you that to you really quickly. So we go to menu on TI Inspire and stats, we can go there, and we can go to distributions, we can go to our normal CDF, and we can say it's from 1, whoop, not 11, 1 to 9 by 10 to the power 999, which a non-CAS will tend to use as infinity. And we've got our standard values in for mu and sigma. Okay, so 0.1586. Alright, so that's, I'd argue that's pretty close to the value we're chasing, which is 0.16. Or 0.16 is close to that true value. Probably be more correct, wouldn't it? You see, if we've got a normal distribution, we've got mu there, it's a standard normal distribution, mu's there at 0, and we've got numbers of standard deviations. Okay, and if it's greater than 1, we're referring to this portion, this area of the graph here. Now, using those approximations from the empirical rule, we would have this middle zone here from which is 1 standard deviation above and below the mean. We would have left over from that, if we went 1 minus that 68% or 1 minus the probability 0.86, we would have that remaining in the whole distribution. So that would be all the remaining stuff outside, and there, I don't want to colour that bit in really, but we're only looking at greater than 1, so really we're only looking at this half of the 32% remaining, or the 0.32. So it's half of 0.32, which is 0.16, and I said before we're awfully close to that, and the empirical rule is empirical, i.e. it's approximate, right? So that makes sense, right? So I just did that without a graphics calculator. The probability is close to 0.16 if we have Z greater than 1. So in conclusion, we can use the empirical rule to help us understand what's going on, and we can use symmetry for the empirical rule plus other things, and we can see that the normal distribution is broken up as such there, and there's a lot of useful applications for this.